Okay, so last week we looked at how to run queries, and then we looked at arithmetic, and we talked about the difference between equals and is. Now what we're going to look at is actually structured sort of data types or dynamic structures in Prolog. So the textbook mainly talks about lists, which we are going to talk about, but we're also going to look very quickly at trees just to show you the kind of variety of data types that you can build up in Prolog. So we can make an example of a binary tree in Prolog, and we just write it out in bracket notation. So this here is actually a representation of that tree. So if you look at the inner elements, if you look at this bit here, you've got tree bracket empty, comma, Jack, comma, empty. So what that means is this is a tree that's got Jack in the middle, and then it has two children, and the children are actually empty and empty. So these are sort of dummy values. And then over here we have the same thing, empty, Jill, empty, and sometimes when we draw the tree, we may leave off the empties. So we may just draw it like this. But secretly there are little empty. So Fred has, this node has two children, Jack and Jill also have children, but they're empty children. So we don't show them. It's just a kind of stub. And so we can build up these structures recursively. We can say tree empty, Jack empty, Fred, tree empty, Jill empty. So that's saying this tree has a root node which is Fred, and then the left child is this tree, and the right child is that tree. So we get this kind of composite tree like this. And using this notation, we can build up trees of arbitrary size. Here's another example of a tree. We've just written it out indented to make it a bit easier to see what's going on. So the left child of this tree is a tree with 7, empty, 7, and empty. The root node has a plus, and then the right child is a tree with minus, and then the left child is empty, 5, empty, and the right child is empty, 3, empty. So some of you may have seen this kind of structure before in a different programming language, C or Java or something. For some of you it may be a little bit unfamiliar, but if you just persist with it, it's not as scary as it first appears. So what can we do with these trees? Well, this is an example of a predicate that just tests whether something is a tree written in the right syntax. So it's saying the word empty is a tree, and then something is a tree if it says tree, and then there are 3 elements, left, data, and right, and the left and right have to also be a tree. So this is like a recursive definition, so we can just use that to test. If we write down a long expression like this and try to see whether it's actually a valid tree, it'll come back and tell us yes or no whether it's a valid tree. Now, we can also do some other computations on the tree. For example, we might want to count the number of nodes in the tree. So we could have a predicate called tree size. And so this is the same tree as before, but we haven't shown the plus and the minus and the 5 and the 7. We're just showing the structure of the tree. It's got the root has a left child, and then the right child has 2 children. And how many nodes are in this tree? Well, 1, 2, 3, 4, 5. So we want something that'll just take a tree in that format and tell us how many nodes are in the tree. And this is actually the program that will compute it for us. There's the code for the tree size on the right, and let me try to get the actual tree on the left here. That's the tree we're going to be working with, and this is the code. Now, this is an example of a recursive program, and a lot of the programs in Prolog are recursive. So we start with a base case. So if the tree is empty, then it has 0 nodes, so the size is 0. If it's not empty, then it must have a left child and a right child, and then there's something in the middle, but we don't care what symbol is in the middle because we're just counting the nodes. But what we do is we count the number of nodes in the left tree, and we call that left size, and then we count the number of nodes in the right tree, and we call that right size. And then we add them together, and we add 1, and that gives us the total size of the tree, and that's what we return. Now, if we just trace through this, we'll have a better chance of seeing what's going on. So the first thing is I've written this into the program as my tree of this. So to save the trouble of having to retype this long expression. So when I say my tree x, it comes back and says x is that tree here. So this is just a representation of that tree. First I have to say my tree x, and then I say tree size xs. And it comes back and says x equals 5. That's the number of nodes in the tree. Okay. Now, if we trace this, we can see what's happening. So first it has to say my tree x. So it looks into the program and says, oh yes, there's a fact that says my tree, blah, 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 blah. So the x must be the blah, 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 blah. So it comes back with this, and then it tries to calculate the tree size. So it says, okay, first of all, I have to calculate the tree size of this left bit, right? The empty 7 empty. What's the tree size of that? And then it comes down and says, okay, well, I need the tree size of empty, which is 0. I need the tree size of the other empty, which is 0. And then I add 0 and 0 and 1, which is 1. So here it's saying that the tree size of this little tree here is 1, empty 7 empty. So that's got 1 node in it. Then it moves on and calculates the size of this subtree. And again, it has to break it down into this side and that side. So it starts with this side, empty 5 empty. So in exactly the same way, that comes back as having the empty is 0, empty is 0. So empty 5 empty is 1. And then the 3 is exactly the same thing. 0 plus 0 plus 1 is 1. So it said, okay, the size of this tree is 1, the size of that tree is 1. So when I want the size of this tree, I add 1, 1, and 1, and I get 3. But then what I originally wanted was the size of the whole tree. So it's 1 plus 3 plus 1, which is 5. So sorry, that is a little bit tedious, but that shows you basically it's doing in-order traversal of this tree and figuring out the counting the number of nodes in the tree. Okay, any questions about this? Okay, but so you can see what's going on, but this illustrates, this is the first example we're seeing of a recursive program. So there's the base case, which is the empty tree, and then this is the recursive case. Yes?
We have set the rule that if it's empty, then the size is 0. But
yes.
Where we set the rule that if it's not empty, it's 1.
In this case, yeah. Right, so this rule here, if L and R are both empty, then these will both come up with 0. And so it'll be 0 plus 0 plus 1. Yeah. So it's not a base, yeah. We could have put a base case. We could have put a base case saying,
If left and right are empty, then it's 1.
yeah, we could have had tree empty, anything empty is 1. We could have put that in, but it's not needed because it can be derived from the other rules.